So I'm starting the yellow board. Okay, so we have regular expressions and DFA. So far, we have trying to intuitively do some conversion between regular expressions and DFA, and homework was related to this issue precisely. Did you have any difficulty, or did you find some regular expression like too difficult? Did you try several strings in order to see if the language was correctly accepted by the machine?
Yes, I have a trouble with the problem 15 in the last letter. I guess that is letter
D.
D. D.
Yeah. So it says something like this. That one, right?
Yes.
What was your question on this, Emilio?
I interpret that there is a chain of letters contain a first X, letter Y, letter Z. So I know that, for example, uh, the letter X will be a zero.
Oh yes, 0 or more
Or
occurrences.
zero or yeah, zero or more X. So equal to Y and equal to Z. So in this case could be a chain that is zero. In this case, I don't know how to represent this chain in the in the diagram.
Oh yes, that's a good question. Actually, what you mean is that if we have 0 occurrences of X and then 0 occurrences of Y and 0 occurrences of Z, then we
Yes.
have the empty string, which we represent by using this lambda, as we said before. So language would be conformed by lambda, and then perhaps one occurrence of X, one occurrence of Y, one occurrence of Z, or maybe two occurrences of X, two occurrences of Y, two occurrences of Z, or even maybe some combinations of them, a lot of combinations, right? So this is infinite, an infinite language. That's why it's very important to say etc. with some small dots here. Of course, sometimes with this kind of description, if we write only this, it's difficult to infer from the list that the whole language is this one. But well, that's not the question. The question of Emilio is how can we say the string? So whenever we have the initial state with empty string, with accept state, then automatically the empty string is accepted. So in this case, this would be represented in this way. Yes.
Okay.
And afterwards, we can say, okay, 0 or more occurrences of X, and then we change to Y. And after this, it's still an acceptance state, an accept state, because we can have 0 or more occurrences of Y. And finally, with Z, we have 0 or more occurrences of Z. So you can, and still there is something that we must take into account. What would happen if we had no occurrences of Y? With this procedure, I am forcing to have exactly one occurrence of Y before having one occurrence of Z. So in order to avoid this, I need to make a bridge like this one and add directly. This will allow to have one occurrence of Z or more, or one occurrence of Y or more, one occurrence of X or more. So with this little bridge, the automaton would be complete. Of course, this is an intuitive method. As I told you before, sometimes we are not sure on how to represent this, or maybe you can say, well, where the hell from does this little bridge come from? Well, maybe if we have a little bit of experience, we know that this must be included. However, as I promised you before, today we will see a method where you don't have to think. So that's a very good news. That's good news, to have a method where you don't have to think, and then you are pretty sure that you are doing things right. Uh, Hopefully life was like that, but no, that's why life is it's interesting. But well, in math, we do have such methods. So today we will see that method. For this, then, well, I think your question is answered, right, Emilio?
Right. In this case, I fall in the diagram. So that's similar, but I put before the first state a first state. So that's why I my diagram is it's incorrect.
Okay, don't worry. That's why homework is for, so that we try things and then to realize what kind of mistakes we can do. Uh, when I ask you to do this intuitively, of course, intuition can make mistakes, and don't worry about that. Well, of course, we must learn to do it properly. So usually, the what will help us a lot to know how to do this is by using the method. And for learning this method, we must take into account, well, I change page. So again, regular expressions and the FA. If you want to look for this in Spanish, well, only change letter. It's as if English was the reverse order, right? Expresiones regulares y autómatas finitos deterministas. This is funny because we are just inverting letters and means the same. Well, except for the and. So maybe we can change this, and okay, no need to change anymore. Well, so in order to build a regular expression, we have three methods, or we have three mechanisms of constructing the regular expression. The first one of them, we have seen it not formally, but we know it already, is called concatenation. This concatenation is represented by this symbol. Sometimes I close the circle a little bit more and look something like this. Well, for the purpose of this course is exactly the same. And also we have another method which, or other construction mechanism, which is union, which is represented by U from union. Remember, we are using sets, and sometimes I use also the bar. And finally, we have clean star, which looks like an asterisk in a superscript. And that's it. No more methods for building a regular expression. So also we begin by the assumption that a symbol is a regular expression, meaning that a symbol is one of these that belong to sigma. We are working, for example, with X and Y, or XYZ, 0, 1, etc. That's a symbol. So as we are defining languages, if we say a symbol is a regular expression, it means that I can build a language. For example, if I say my regular expression is A, this is regular expression. And we will put to the right the language this is defining, and the language defined by this regular expression is this. I'm writing this in order to stress notation, to point the correct notation, because a regular expression expresses or states a language, but no curly braces are needed. Why? Because this implies that this is a set. When we consider the set, we need to write these curly braces. So in this case, A means different things. Well, in this case, this is a string, but this is implicitly, this is a set because we said before this is a regular expression. I hope not to confound you. Just remember that regular expressions do not need curly braces, but they do define a set. Yes, with more examples, I think this will be more and more clear. So it says a symbol is a regular expression. Maybe, sorry, I confounding you because my symbols were X and Y. So let's put it X or Y. So this is a regular expression. Then we have that concatenation of any regular expressions is a regular expression in turn. So if I combine one regular expression with another regular expression by using concatenation, then the result will be also a regular a language, a regular language like this one. So I'm concatenating X and Y. I can do this because I'm sure that X is a regular language and Y is a regular language. If I concatenate both of them, then I have a new regular language. The same will happen with X or even X again. So I have X, X, etc. So far, these languages I am building have only one element, one string. But what happens when we use the union operator? For example, let's say I have a regular expression here, and the union with other regular expression, then this means I am accepting two different strings. Or if I say y and x, well, this is exactly the same because remember that order is not important within a set. Or if I use the union on the same set, well, we have only just one x. And finally, the clean star looks much more interesting because we already know that it means zero or more occurrences of the language that is before. So this would mean that we have from 0 to 1, 2, 3, and more repeated, more times repeated repetitions of the regular language that is just before it. So please be aware that each one of these is in turn a regular language. X is a regular language in this context. And of course, X is also a symbol in this context. Yes, so maybe sometimes this makes you a little bit confused, but just remember that regular expressions define languages. And at the right part here, we have the language disclosed or maybe expressed with most of the examples we have. We have been doing this several times, so this is not new. However, now we are comparing both sides, from the left side and the right side. And this is important. It is important to state this because if we follow this chain and we say a symbol is a regular expression, any concatenation of two regular expressions is a regular expression itself. Any union of two regular expressions is a regular expression as well. And the clean star of any regular expression is a regular expression as well. So by this means of combining regular expressions, we assure that we will have always a regular expression. Whatever is added to a regular expression maybe will not guarantee we still have a regular expression. For example, intersection. Intersection of two regular languages is a regular language. Well, demonstration is left to the reader, or we will see an exercise afterwards, okay? So to make it short, too long, didn't pay attention. The short part of this is regular expressions are made of symbols, concatenations, union, and clean stars. That's it, yes? We have been using them, as I said before, intuitively. However, now that we want to link them to the construction of DFAs, in order to do this, we must demonstrate that each one of these steps yields actually a DFA. So let me just move a little bit down this part so that we have more space. Oh, let me move this below. That's it.
I'm sorry, Professor.
Please.
I'm sorry to interrupt you, but Dima is trying to connect to the class and he cannot.
Oh, poor Dima. Let me see what happens. Maybe is he? Let me see. I cannot see participants. Give me a second. I cannot, okay, I see. I wonder why, because I cannot see him on the in the waiting room. So the link is the same as always. Maybe he needs to restart his client, because from this side, I don't see anything unusual. So please ask him, Oksana, if he can close his Zoom, open it again and try to connect. Maybe he has better luck with that.
Okay. Also, he's asking maybe he could use a password of conference.
Okay, yes. Give me a second. Okay, so what we will do now is convert each one of these strategies into a DFA, meaning, for example, that showing that I can build a very simple DFA that can accept a single symbol. So this is no problem. I can accept X, or I can accept Y as well, as you can see here. And hello, Dima. Nice that you were able to connect. Okay, so we have here one automaton just to recognize X or just to recognize Y. No problem with this. So we are showing that we are able to build an automaton out of each one of these. For concatenation, every time we have concatenation of a machine, let's say we have some machine that has a start state, and inside it has be joined an empty transition. This empty transition will be represented with epsilon. This epsilon will mean that we can change from one state to the other without having to read one symbol from the input. And before doing this, sorry, I will show you machine 1 and machine 2. So this is machine 1, machine 2. If we want to concatenate machine 1 to machine 2, oh, sorry. We want to concatenate the language of machine 1 with the language of machine 2, then what we have to do is modify both machines so that the final state is connected to the beginning of machine 2 by using an epsilon. We will do some exercises related to this afterwards. Now it's like the general way of doing it. With union, we will have a similar fashion. We have two machines. We will have here the same kind of machine, which has a beginning and has an accept state. And here we have, again, another machine and the accept state. So in order to build the union of these two machines, we will add a new initial state. Sorry, let me draw with different color. So we will draw here a new initial state and then connect to the previous initial states by using, again, epsilon symbol. Don't worry now if you say, what the heck is that epsilon symbol? We will see now, just hold on. And finally, to build the clean star, we will have another behavior, a little bit more complicated, but not that much. Let me show you. Let me, again, take some space. So in this case, we will have, again, the core or the old machine, which looks like this. It has its accept state. So for doing this, and sorry, very importantly, this accept state will not be longer an accept state, and the only accept state, the new accept state, will be this one. In this case, we keep both accept states. Okay, sorry for going back and forth. Okay, so for doing the clean start of a machine, we need to add a new initial state and connect to the previous initial state by an epsilon. And also we will move the old accept state to a new accept state, so that this is no longer the accept state, but it still exists as an state. Then we will create a loop that goes back from the original accept state to the original initial state of the machine. And also we will add a bridge to from the original, from the new initial state to the new accept state. All these new arcs will be labeled with the epsilon, with an epsilon. And that's it. With this method, we have the ability to convert any regular expression into a non-deterministic finite automaton. So until now, we are creating an NFA. This is the first step. The second step will be to convert the NFA to a DFA. Why? Because we want to have it a deterministic finite automaton. Of course, there will be something new to the method we saw before, because now we have these strange things, these epsilons. So let me, now that we have seen this theory, let me try to explain this again with an example, and I think it will be clearer to you, okay? So I will change page. Have you taken note of this, or screen capture, or whatever? Okay. It's better if you take notes, because the mechanical way of having to draw what you are seeing helps into remembering and learning. And sometimes just a screenshot and you say, what was this? So I suggest you to take notes, but of course, each one has their own method for learning. Or as Arturo, you can just go back and draw it in the blackboard. That's good as well. Well, whiteboard in this case. Yeah, nice. Okay, so let's see an example. What if we go back to those examples that we already did, that we made last class? So let me go back. What about, which one? Not too complicated. Or, I don't want to start with a very complicated example. So let me create a new one, because the ones we did before are a bit complicated. Let's say oh my God, A or no, X and Y, X or Y, and clean star concatenated with X. This has exactly one of each operation, and it shows us how to build the NFA out of this regular expression. So we saw that we have to start by building the initial machines that are the simplest ones, that are those that recognize each one of the symbols, meaning that we have one that recognizes X, one that recognizes Y. And that's it. Now, the method says, now if you have a union, well, remember please that whenever I use this bar, it means union is exactly the same. Sorry for mixing notation, but anyway, you will find it the same in different books. So it says, now add a new state, and from this state, connect the other ones by using an epsilon transition. How does this looks, or what does this imply? This means that if I'm on this state, I can choose arbitrarily to change from here to here without having to read anything from the input string. Let's suppose that my input string says X. Then suppose I start here and then I read the X. If I read the X, maybe I go into the pit, X and Y, And then I can say, oh my God, I read an X and I was not able to accept this string. This is possible. However, I have another choice. The other choice is I'm here, I just jump from here to this state just because I wanted, and then read the X. And then, oh yes, I end in an accept state. So maybe you will be wondering, well, then how can I choose? Well, you don't have to choose. You must try all possibilities. If one of those possibilities after reading the string takes you to an accept state, then the string is accepted. Only with one possibility that ends in an accept state. Of course, there will be a lot of ways where this string is not accepted. Another way of having it not accepted is being here, jump to this state just because, and then try to read the X following the invisible path because now we know it's implicit to the pit. And then we will say, no, by doing this, the X is not accepted, right? Because I end up in a non-accept state. However, remember that there's still just one way to accept this X, and this one way is this one. So this is what happens with the non-deterministic finite automata. And remember that before, in order to convert an NFA to a DFA, meaning non-deterministic to deterministic, we can do this by exploring at every moment all different possibilities. That's why the last class we saw a method that consisted on making the union of all states where a symbol can take us to. Do you remember? So that represents that we have to explore all possible or all different options. We will convert this to DFA afterwards. For now, don't worry. We are working on converting the regular expression to NFA. So now we are on the phase of regular expression to NFA. Afterwards, we will concentrate to convert this to DFA. But now we are here. Okay, so okay, let's forget all this. All this discussion was only to show you that there are many ways to not accept X, but there's still one way, and with this one way, we can say we can accept X. We are accepting then this, we are working on this part only. Now, we must do the clean star of all these things. Yes, in Spanish we would say of all these mother, but no, we are speaking English. So we need to do the clean start of this. As we draw before, I did some kind of a box like this, do you remember? So that with this box, we have only one one initial state and one accept state. So I still need to modify these ones to the right so that I have exactly one accept state. So for this, I add one accept state, connect it with epsilons, and remove the original accept state. So at every point, each one of these machines will have one initial state and one accept state, no more. And at each point, I can assure this by, or ensure this by adding things like this. So this newly created machine has one initial state and one final state. If I have more than one final state, I just join them with using into a single one by using epsilons. Yes, is this step clear? So that my boxes will have always only one initial state and one final state, one accept state. That can be guaranteed that it can be built always. We are able to do this at each step. So we are here. Now, for this, we will apply the, clean star. I will use a different color to make it a little bit clearer. So to add the clean star to an existing machine means I need to add a new initial state, connect to the previously initial state by using an epsilon, and then create a new final state by using an epsilon as well and removing the original accept state. This is one of the first parts. Then I need to add another arc which goes below, which connects the newly created initial state to the newly created final state. And also I will add an arc that connects the previously accept state with the previous initial state, and also with an epsilon. So this must look like an UFO. If it does not look like an UFO, then it's wrong. ¿Sí? Se debe ver como un ovni. Si no se ve como un ovni, es que está mal. Well, not true, but essentially it resembles an UFO, like a little spaceship where this goes back and the alien travels here inside. Well, don't listen these things. Okay, now we have covered up to this part. Yes, we have now this clean star of X or Y. And finally, we need to do this other part, which is the concatenation of X. To do the concatenation, we need to apply just a last step. And now the big machine will be this. Let me erase this part. The big machine will be like this. And again, please observe that we have exactly one initial state and one final state. So it's compatible with all other processes. Always one initial state, one final state. So what we are doing is by building a greater machine with blocks that have only one initial state and one final state. And the final concatenation needs then to consider the other machine. The last machine looks like, let me draw it this way. The other machine accepts just an X, and that's it. So the algorithm says, in order to concatenate two different machines, what you have to do is to add an arc between the accept state and the initial state of the second machine, and erase, this is too big, and erase the previous accept state and the new accept state by this one. Leave this as the accept state. And that's it. And now if you want, you can see all this like a new box that has one initial state and one accept state. So we have finished now. This is the method for obtaining an NFA, non-deterministic finite automaton, out of a regular expression. Before converting it to a DFA, let's play with it to see how it works. So let's make it run. In order to process it or to verify its way of working, let us see what kind of strings this regular expression accepts. For example, it says X or Y repeated any amount of times, let's say X, Y, X, and concatenated with an X. So this is an example of a string that must be accepted by this automaton. So we start here and we will try to follow the epsilons so that we can accept this string. So we go epsilon, epsilon, then I accept this X, then we say, okay, accepted. Then I need to accept another Y, so I move to this place, move to this place, move to this place, and accept a Y. Okay, this is red. Now I am here, and I need to read another X. I go back to this place, go back here, I have an X, and I read this, and then I'm again here. Now I have two options here. That's why it's non-deterministic. One is to go back and read the final X, but that won't take me to an accept state. We want to accept this string. Well, we must look for all different options in order to accept a string. So if we see this, we know that in order to read that last X and to end up in an accept state, I would need to go this way. Epsilon, another epsilon, and then to read the X. I reach the end of a string and I end up in an accept state, meaning that this string can be accepted. Yes. So if you are wondering, how do I know if I follow or not an epsilon? Well, it's just by looking the diagram and trying to read each symbol so that it will take me at the end to an accept state. That's what I'm looking for. Yes. But also there is, again, there's a method that allows me not to think. And that's always good because we have a professor in SIG that says thinking hurts, pensar duele, and he's the head of the Artificial Intelligence Laboratory. He's Salvador Godoy. He says, oh, I know, thinking hurts, so better do not think. Well, but we must think. Okay, so up to this point, are we clear? Okay, clear.
So the epsilon is a way to transfer from one state to another without reading any symbol.
Yes, right. And it's called the empty symbol, which is very similar to the empty string. Just to make this this clearer, suppose we have an epsilon, and this is equivalent. If we have a string made up of an epsilon symbol, we have an empty string. So this is empty string, and this is empty symbol. If I concatenate two empty symbols, I have one empty string. If I concatenate two empty strings, I have an empty string. So as I told you before, you have to be in a Zen mode because we are working with nothings and infinites. However, just think that this represents a symbol, and of course, a string with no symbols or a string with any number of empty symbols is still an empty string. Yes. Una cadena vacía puede estar hecha de símbolos vacíos y puedo concatenar los símbolos vacíos que quiera y la cadena sigue siendo cadena vacía. Entonces, puedo definir una cadena vacía formada por 10,000 símbolos vacíos y sigue siendo una cadena vacía. También puedo concatenar dos y sigue siendo una cadena vacía, ¿no? So it's like adding nothings. Nothing plus nothing is nothing, and you can make another nothing out of many nothings. It's sort of that. And also, please observe that because this is equal to this, Brookshire likes to use lambdas here. So if you go to Brookshire, you will see lambdas, lambdas, lambdas here instead of epsilons. And you will say, oh, what a big confusion. Why does the teacher do this to us? Well, it's not against you. It's just to clarify that it's better to use epsilon because the transition you have here, all transitions must be tagged with a symbol, not a string. What we have here always is just a symbol, 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 symbol. So if I add an empty string, well, it means the same. The final result is exactly the same, but it's more correct to add here an epsilon. And you will see that other books, such as Zipser, that's another book for automata theory, those like this. Yes, so we will follow this because it's more exact to this nuance, to this small detail. Okay, so going back to this, well, we now have a new toy we built from this thing, and we have executed this toy to verify that a string is accepted, and we verified it's accepted. And now we will see how to convert it to a DFA. So out of this, I don't want to say awful thing, but complicated thing, we want something simpler that is deterministic. In order to do so, I will change page. I will try to steal this one and copy to the next page. Okay, here it is. let me simplify a little bit by erasing those parts that are not needed. For example, this box is not needed. That's it. And also I will move this closer to the other part. So it's exactly the same, just like this. And of course, the initial state. It's the same one, just a little bit more compact. Okay, in order to convert from an ENFA with epsilon transitions to a DFA, we will use exactly the same method we saw before, just with one modification. And this modification will handle all those epsilon transitions. So do you remember the first step of the method was number your state? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. With this, remember that the numbering is arbitrary. Just start with 1, and then you can do whatever you want. You can do 1, 10, 9, 8, etc. No problem. There are just labels. Okay, and pay attention, please. Now we will do the following. We start with state 1, but now before we start merging states for destination, we will merge before, because when I am standing on state 1, I can reach states 2, 3, and 4. Then I need to merge state 1 with these states. Imagine that this is a single and a big state, and also, of course, 8, and then 9 in turn, and that's it. So the question is, which states can I reach from 1 by following only epsilon transitions? So again, standing on 1, I can reach 2, and in turn, I could reach 3 or 4, and also I can reach 8, and in turn, I could reach 9. So we will write all those states. We will merge them here. So I write 2. From 2, I can reach 3, I can reach 4, and also from 1, I could reach 8, and also from 8, I could reach 9. That's it. So it's a very big state, yes, but we are merging a lot of states just because I can reach them by following epsilon arcs. So no dark magic here. We are just following epsilon arcs. And that's it. Now that I have finished doing this, then I can close my state, and then I will apply my algorithm the same way as we did before. That means let's work on this state and work for the arcs. Where do I go with an X? Okay, so 1 with X, nothing. 2 and X, nothing. But 3 and X, yeah, we go to 5. So I start writing 5. I leave this state open because we will merge it with other states. Not now, not yet. We keep doing this. We were at 3. So we have verified 1 and X, 2 and X, 3 and X. Now 4 and X, this is nothing. Okay, verified. What about 8 and X? Nothing. Okay, verified. But 9 and X, yeah, 9 and X goes to 10. Then I have to add 10 to the list of states that where I can go to from this state. Okay, still I will leave this open because it will be extended in later stages. But for now, I need to keep this and now examine for Y. So now let's do exactly the same for Y. Let's erase those little dots because those were for X. And let's verify for Y. 1 and Y, nothing. 2 and Y, nothing. 3 and Y, nothing. But what about But what about 4 and y? 4 and y takes me to 6. Then it means I will add 6 here. Good. 8 and y, nothing. And 9 and y, nothing. Okay, then it seems we are done with this state. We change it to green color. Now I have to work on the other states. If I want to work with this 5 and 10, first I need to explore the epsilon arcs. So the epsilon arcs say, well, standing on 5, what other states can I reach by following an epsilon arc? So you can see 5, and with epsilon I go to 7, but 7 goes in turn to 2, and 2 goes in turn to 3, and 2 goes in turn to 4, and it seems that that's it. And of course 7 goes to 8, 8 goes to 9. So well, that's a lot of states. Well, we need to add all of them. So let's review. From 5, reach 7. So we add 7. From 7, we reach 2. And also we reach, well, let's do from 2, 3, and 4. And that's it. And then from 7 also we reach 8. And from 8 we reach 9. And I think that's all. Yeah, a very, very big state. But that's not all, because that's the expansion of 5. Now we need to add the expansion of 10. So we verify 10, and there are no arcs coming out from 10 to other states with an epsilon arc. But also note, please note that 10 is an accept state. Then it means that all this state will be an accept state. Like this. Okay, we have finished the expansion for this state. And now we need to examine where do we go to with X and with Y for each one of those states or substates that compose this mega state. Yes. So 5, let's examine with X, and we will see what happens. 5 and X, nothing. 10 and X, nothing. 7 and X, nothing. 2 and X, nothing. 3 and X go to 5, then 5. 3 and X go to 5. 4 and X, nothing. 8 and X, nothing, but 9 and X goes to 10. So we can see that this is exactly the same beginning as this one, right? And when I expand this one, it will be exactly the same expansion. So this means it's a loop. With an X, I go back to this same state. So I will erase this and draw it accordingly. So like this, X. Okay, and what about Y? Let's check it. 5 and Y, nothing. 10 and Y, nothing. 7 and Y, nothing. 2 and Y, nothing. 3 and Y, nothing. 4 and Y, yeah, let's go to 6. So 4 and Y, go to 6. 8 and Y, nothing. And 9 and Y, nothing. So we have this is exactly the same as this one. So we will point this Y to the state below here. But the state below is unfinished. We will work on that now. But now this is done. Why? Because I have checked all for X and all for Y. Now, last one. We will check this one. 6. We need to check first the expansion of 6 and examine all states that 6 takes to by following an epsilon arc. So 6 will lead us to 7. 7 will lead us in turn to 2 and 3 and 4. So let's add it. 2, 3, and 4. And also 6, 7, 3, 4, and then to 8, and in turn to 9. And that's it. The expansion is done, so we can close this state, but now we need to check for X and Y. So let's check. Okay, this and X takes me to, and 6 and X, nothing, 6 and X, nothing, 2 and X, nothing, 3 and X, nothing, 4 and X, nothing, 4 and X, nothing, 8 and X, nothing, and 9 and X, 10. Like that. And it seems that's it for X. Then we...
Excuse me, teacher.
The
Sorry
tree.
for the interruption, but the state 3 leads to 5 with X.
Oh, and it's included. Yes, right. My bad. Thank you very much.
Yeah.
So let's write again. Sorry, 6 and X, nothing, 7 and X, nothing, 2 and X, nothing, but 3 and X goes to 5, as you correctly pointed. Thank you. And 4 and X, nothing, 8 and X, nothing, and 9 and X, 10. So we have a combination of 5 and 10 with X. So again, we know this is the same beginning as this one. So instead of creating a new state, we go up to this one. So I erase and then go to this state with X. And lastly, what about Y? So let's examine what happens with Y. 6 and Y, nothing. 7 and Y, nothing. 2 and Y, nothing. 3 and Y, nothing. But 4 and Y goes to 6. And 8 and Y, nothing. And 9 and Y, nothing. Okay, so again, this is exactly the same beginning of this state before expanding it. So it means this is a loop. So let's reflect that. So we do this and Y. And we have finished. Oof, so this is the price for not thinking. We have a lot of hard work to do. So I don't know what's worse. I think I prefer thinking. It was a little bit heavy, but I hope for you was not also so heavy. But now we have, this is a DFA. This is the good part. A lot of effort, but we have now our dear DFA. So does it work? Well, let's try it. Let's try it first with the same string we had here, x, y, x, x. So we have x, y, x, x. So let's see, x, y, x, x. Oh, fabulous, it was accepted. Now, let us remember the regular expression this was taken from. It was something like this, and then concatenated with an x, right? So with this, we can check, well, what if my string does not end with x? Let's add a y. What would happen? Okay, x, y, x, x, and then y. Oh, great. We are not ending up in an accept state. So it works. Also, a question for you. Does this regular expression accept the empty string?
No.
No, because there is an X in the end.
Right, so the smallest string this regular expression accepts is an X. Let's try. What if I just write an X? Okay, X. Wonderful. Accept state. And what if we have, I don't know, y, 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 x? It should work. Y, 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 X. Well, it works. Of course, we are not demonstrating by trying trial and error, right? I want to show you that some strings that we can think of, yeah, they really work. The real demonstration that this is equivalent to this one is the method we are using to build it. So maybe the method is a little bit, how to say, laborioso. It's hard work to obtain this one, but it's guaranteed that you will be able to always convert a non-deterministic finite automaton with epsilon transitions to a DFA. So just to recap, last class, in Tuesday, we saw the algorithm for NFA to DFA. Yes, and today we have just learned this algorithm, how to convert an ENFA with epsilon transition to DFA. So in order not to torture you more with my voice, so it's time for you to work on some exercises. So let's start precisely with the one of the homework, thanks to Emilio. It says something like X concatenated with Y, and then this is concatenated with Z. So please apply the method we have seen today, which consists on first having a machine that accepts X, then adding the clean star for this X, then creating a machine that accepts Y, adding a clean star that accepts this machine, then concatenating both machines, and then concatenating with the machine that accepts the clean star of this other language. So maybe you don't have to do step by step, or do you not have to show that each step was taken. You can work just on the solution. But yes, please use the construction, the block construction we saw before. So what I want to see is first the NFA with epsilon transitions, and then you will convert it to DFA as well. So if at any point you have any question, just speak. I will be here.
Can you show me the previous slide?
Yes, I will leave that one, okay?
Okay.
Maybe I should write the exercise here so that you can see both things at the same time. So here. So this is Windows 95, I guess. Let's make something more fun. This is too mechanic. Well, we have to know how to do this. However, I want you to apply this knowledge now you have on regular expressions. Surely you have been using regular expressions on your programs, on your, I don't know, even Java has some module to process to process regular expressions, which is horrible, by the way, but well, it has. I don't know, Python is less ugly, but if you want to do regular expressions really, truly incorporated to a language, maybe you can use something like Perl, but now it's perhaps a bit outdated, but it has native support for regular expressions. Well, but I will ask you to program something using regular expressions. But for this, let's add some context into it. We will write a chat machine, oh, yeah, a chatbot called nowadays, and we will implement it using only regular expressions. So first we need some definitions. I will share my screen. What it means to to talk, well, sorry, the slides are in Spanish, but I will be speaking in English, so I think there will be no problem. So to talk means to converse, to talk, to communicate, and usually the process of talking is very, very complicated because you have some very complex structures in your mind, in your brain, and they are passed linearly through language, through text, which is like a linear transmission. And you want to have the other person to have the same structures that you are trying to convey. Well, this is a kind of simplistic model for conversation, because we never will be able to project into the other person exactly the same what we are thinking, because all of our concepts, even the most common ones, have little nuances, little differences, because each one of us represents concepts inside related to all the experiences we have since birth. So it's really wonderful that we can communicate even given these differences. Well, is it possible to talk with a machine? Well, this is a question that has been asked many, many times, and maybe you can try to talk with your Roomba and ask it, please go there, and there is more dust over there, and the Roomba seems to understand, and yeah, it goes, but it's only because mere coincidence. But well, sometimes we have that feeling, or maybe not all of you, but sometimes, that we tend to talk with objects or unanimated objects because we want to communicate with other things the same way we communicate among humans. And of course, there is a plethora of assistants, you know, Siri or Alexa, and all those chat things. But well, we will try to do something like that now. And of course, this has been an interest of people, human beings, since many, many years ago. We have here the Galatea of Pygmalion. It's a Greek myth where Pygmalion was a sculptor, and he wanted to sculpt the most beautiful woman he could on marble. And he did. However, when he finished, he was so astonished that he went in love with his creation. And very much alike as the Pinocchio tale, he asked the gods to make it real. And you know, the Greek gods always listen to some people, and in order to play with them, because Greek gods are very playful, so sometimes not a little bit mischievous, not in good mood, they say, okay, I will make your Galatea alive. And it became alive. And then this illustration shows how now the new invention, the new thing to interact with, also it's giving back ideas to his creator. So, well, it's an interesting way to put it. Just I want to stress or to mention how this has been an interest since ancient times, and replicated and repeated in many other myths. Surely, maybe you can think of something similar, where we want to make unanimated things alive. Another example are the Hephaestus automata. Very different concept of automata that we are studying here. It's just because they can move by themselves, and it says they are metal statues, and Hephaestus, which was the god of metallurgy, gave them the power to move, to have some kind of autonomy, and even they could defend other people from attackers. It's like if we wanted to have something that is alive but serves to us and is mechanic, well, there are a lot of motivations. Also, we can consider the Jewish golems, which are for protecting or defending even some places, or the Paracelsus homunculus, which was the desire to create human or pseudo-human things outside of the uterus. So it was like mixing men seeds with other things, silver, and doing some alchemy. so that at the end you have a little man growing on that probe, so that it grows, and at the end it serves to you. Well, just this is only motivation, but what I want to reach to is this. Has any one of you heard of Eliza? ¿Alguno de ustedes ha escuchado de Elisa? No one, okay. Eliza is a historical chatbot program. Actually, is known as the first chatbot program because it's very old. You can see 1965, and it emulated a psychologist. It says a psychiatrist. And the kind of dialogue it used to have looks as the one over there. Eliza says, "What's your name, dear?" And there's some people who says, "Amit." "Hi, I'm Eliza. What do you want to talk about?" And Amit says, "Can I talk about my problem?" "Sure." Amit says, "Due to ongoing exams in college, I have a lot of stress." And Eliza says, "Please relax a little, sleep well. Thanks for your advice. No mention. Bye and keep in touch." So, well, it's surprising. It looks like it's presenting empathy, like it's understanding the patient, and we don't know why or how, but this caused a lot of emotion and a lot of buzz in the academic circle, because it was considering that machines could apply therapy to humans. Well, what was behind of this were a lot of theory. Well, we have another, I think we have here another dialogue. It's in Spanish. I will translate it quickly because I think it's very interesting. And Eliza says, "All men are the same." So we can assume the patient is a woman and complaining on men. "All men are the same." Eliza asks, in which sense?" And the patient says, "They are always bothering us for one cause or another." Eliza, always in green, says, "Can you give me a specific example?" "Well, my boyfriend made me came here." "Oh, your boyfriend made you come here?" "Yes, he says that I'm depressed most part of the time." "Oh, I'm sorry to listen you are depressed." "Yeah, that's true. I'm unhappy." Eliza asks, "Do you think that coming here will help you not to feel unhappy?" "I need some help, that seems." "What would you mean for you to have some help?" "Well, maybe I could learn to take along well with my mother." "Tell me more about your family." So you can see here, like, wow, it's understanding the patient. How come? And it's the most advanced chatbot I have seen in my whole life. Well, it's just an illusion, of course. I don't want to spoil it, but it's just an illusion. And here is where where the secret lies, because there are some patterns. The pattern says all X are Y, all men are the same. So every time you hear this phrase, all X are Y, you can ask, in what sense? Yeah, try it. Even if you are talking maybe in English and you don't understand, all borogoves are seamless. Ah, in what sense? And you don't know what a borogove is, and you don't know what seamless is. But you can ask that and you are into the conversation. So these are also tips for keeping the conversation on, despite you are not understanding anything. And always X. So anytime you hear someone saying always X, you can ask, can you give me a specific example? I'm always bored at home. Can you give me an example? I'm always angry in traffic. Can you give me one example? And it will work always, because it's a good answer related to always X. Another one is depressed. So this is a keyword. If you detect the word depressed, then as you are a therapist, you need to say, oh, I'm sorry to hear you are depressed. Or even someone else, my mother is depressed. Oh, I'm sorry your mother is depressed. My teacher is depressed. Oh, I'm sorry to hear your teacher is depressed. Yeah, and it will work always as well. Another keyword, unhappy. I'm unhappy. Then it's I am X, and X is a negative thing. I'm sad, I'm unhappy, I'm stressed, I'm anything. And then you can ask, do you think coming here will help you not to feel eh? And it will work always as well. I need some help. Also, this works with I need X. I need a new phone. I need a new computer. I need more computing power. I need a glass of milk. And for all those assertions, you can ask, what would you mean for you to have X? Yeah, and it works. What would you mean for you to have more computing power? What would you have? How would you mean for you to have a glass of water, a glass of milk? And yeah, you are having a dialogue, you see? So all of these are pattern tricks. And the final one, the last one of this example says, tell me more about your mother. And each time you detect a keyword related with mother, father, son, daughter, brother, sister, tell me more about your family. Well, it works as well, you see? So this is a conversation-led pattern-led conversation. You have a pattern and then you can have a conversation and it works. And also you can try it for Japanese. Well, this is a joke, but Japanese people like a lot to say naruhodo. And naruhodo means something like, yeah, in fact. So you can say, I don't know, in my country, we have pyramids. Ah, naruhodo. And also we are always fighting with each other because we are too many. Ah, naruhodo. And also we have all those that are in the upper part and they say, ah, hi, omashiroi ne. Well, so maybe I met some Japanese people and they seem that they seemed always to say, ah, yes, yes, oh, how interesting this is. Oh my God, yeah, yeah. But they were not understanding, and of course they were not caring at all. So, well, it sounds for me a little bit like Eliza, like, keep on talking, Mexican, yeah, we love you, yeah. Well, naruhodo. Okay, so why do this kind of talking work? Not the Japanese one, but the Eliza one. Why does this work? Well, there is a psychologist called Carl Rogers. He was very famous and is the one depicted here. And he says that in order to have a good therapy, you should make the patient to express using, using reflecting his or her own sentences. For example, the patient says, I went all day long to cycle, or I went cycling all day long. And then the psychoanalyst says, tell me about cycles. So as you can see, it's like a very Eliza way of asking things. And of course, it's not because the psychoanalyst does not know about bicycles, but he wants to know how the patient thinks on bicycles. So maybe bicycles mean something for Christian, but for Cesar mean nothing. Maybe Erica loves cycling, but Paulette hates it. So the concept of cycling will vary between Erica and Paulette. Yeah, but that will come out when you say, tell me about bicycles. Oh, I hate them because they are of no use. They are ugly, I don't know. Or maybe, oh, yes, they are wonderful, but I hate cars, etc. So this is assuming that the patient has a conversational objective. So the goal is in the patient, not in this case in Eliza. That's why it works, and it works well. It works nice. Eliza ran on a machine like this. This is an IBM 7094 at the MIT, and that man over there is Weissenbaum, the creator of Eliza. And here we have him in another picture, and he is chatting with Eliza. And this is a nice picture because you can see how chatting with a chatbot was in those times. This is a teletype, which is kind of electric typewriter, and the result comes out as a printed sheet. There were no monitors, or well, they were, but they were not connected as terminals in those times. So the easiest way to communicate was by using a printer and a keyboard. yeah, very ancient, very old. And even you can see here down, here below, you can see a dialing disc. Maybe you don't know, you don't even know what it was for, right? But it was for dialing numbers, for calling the phone. Well, maybe younger people or maybe your little nephews won't know what a dialing disc is. But don't worry, technology changes, we must adapt to the change. So this model was created by Weissenbaum because he was wondering if machines could think, if the human thought was computable. And of course, we cannot give an answer right now. We won't give an answer in this course because it's not the main goal of this course. However, I'm presenting this because I want you to build an ELIZA. And how? Well, now you know regular expressions. This is from the original paper from Weissenbaum, and his way of writing regular expression is a bit ugly, but I want you to present with the original source. So the pattern says something like 0, which is a variable, u is a variable, me. And then the transformation, the result would be what makes you think I, and 3 is the third position, so it's 1, 2, 3. So here there's a variable, like how can we make an example of this? Rocks, no, it should be a verb. You hate me. I see you hate me. For example, I see you hate me. And then the answer will be, what makes you think I hate you? You see, it's number 3. 1, 2, 3. The zeros only mean anything. Yes. Well, it's hate me. And also clean, 0 means clean start because it can be any number or anything that substitute that. So I hope you, with this very bad example, very short example, you have an idea of what I am asking to you. I want you to make these kind of patterns and to implement it in a very short program that talks to you. It will detect what you say to it, and it will give you back some answer depending on these patterns. For example, what's your name? My name is Heriberto. Okay, then you have to detect the part of Heriberto. And hello, Heriberto, how are you? I'm fine, thank you. And I'm glad to hear you are fine. Why? Because you have some program that if it says fine, well, good, etc., you will see that it's a good thing or a bad thing. I want you to make this simple. I don't want you to program a very complex chatbot. If you want to do that, however, you can maybe go to Pandora bots and try to implement something. But what I'm asking you is to implement a quite simple chatbot. You can even look for the original code of ELIZA, which is not so long. I think it's no more than 100 lines long, and examine it and change it. How will you change it? Well, you need to give some personality to ELIZA. You will adapt it to your own purposes. And also you can make it, for example, talk on cats. I don't know, maybe it's a cat therapist or something like that. So you can be inventive. So the main goal of this is use regular expressions to detect patterns. And you can do it on any language you want. Even Java, which is horrible for handling regular expressions, but if you want to do so, well, I won't say no, but I won't recommend it. You can use Perl. Maybe I will post some instructions on Perl because it handles regular expressions very nice. However, you can use any language you want. Julia, I think, is a nice modern language that handles regular expressions quite nicely. So of course this you will have a lot of time to work on this. I will ask to submit this after April holidays, so it will be for something like April 12th. So you have near 1 month to complete this. I think it's not so elaborate. For this, you need to think, you need to invent, and then you need to apply regular expressions. So this is what I wanted to tell you, and I wanted to give you the context of what ELIZA is, why it's important that you will be playing with this, and of course it will have some errors. Of course it will answer wrongly in some cases, because it's normal, it's usual to have errors for this kind of program.